collaborators. Okay. Yes. So I will tell you something that kept my collaborators and myself quite busy over the last couple of years. We studied the cosmology of axions, and in particular, we studied carefully the production of thermal axions, as the title suggests. And not only we studied the production, but also we connected these results with the observables. So before going back in time in the early universe and giving you the details of our calculations and the implications, I would like to tell you why it is important to think about axions nowadays. So I will start by putting my work into some broader perspective. And this introduction hopefully will be beneficial to those of you who are not familiar with the topic, because I assume that not everybody works on axions in the audience. And so I will set up the notation and I will introduce some concept that will help to understand the implication of our study. So I am trying to switch slide. Very good. So the axion is a hypothetical new particle that arises within theoretical frameworks, trying to solve two issues within the standard model: the observed evidence of dark matter and the strong CP problem. So the first problem is rather well known. If we look at the energy budget of the universe, we understand only 5% of the cosmic pie, 27% is accounted for by dark matter, and the remaining 68% by dark energy. So the axion is a hypothetical dark matter candidate, and the way axion dark matter works will be explained shortly, okay? The strong CP problem is something perhaps less common, so I will spend the next couple of slides on it. And the name axion originated from the ability of the axion itself to clean up QCD from the strong CP problem. So as you can see from this picture, it was named after a famous detergent that was popular in the US in the 80s. And because the axion is able to kill two birds with one stone, it's the subject of an intense research program both theoretical and experimentally. So the strong CP problem, what is the strong CP problem? It's a dichotomy between an experimental fact and the consequence theoretical implication. So from the experimental point of view, strong interactions appear to be symmetric if we flip the arrow of time. So they preserve T, or in agreement with the CPT theorem, they preserve CP, so the combined action of charge conjugation and parity. And of course, this statement comes with an experimental error. So once we try to reconcile this statement with the theory, we have to set the theta parameter of QCD to a value which is less than 1 part in 10 billions, to an insanely small value. So I would like to spend a couple of more words about these theta parameters and how he enters the QCD Lagrangian, so we understand why it's strange that he has to be so small. If we look at the Lagrangian of strong interaction, so the Lagrangian of QCD, all the good and known stuff like the gluon kinetic term and the quark kinetic terms and real masses, something that you usually find in textbooks the first time you study QCD, they are CP preserving, but there are also two operators that violate CP. The first one is the so-called theta term, which is proportional to G dual. G dual is the dual field strength of the gluon. And then there is a overall phase in the quark mass matrix. This is not the CKM phase. This is an overall phase in the quark mass matrix. Actually, these two operators are not independent. You can always perform quark field redefinitions and see that this combination is left invariant. So you can either put all the amount of CP violation in the first one or in the second one, and it will be proportional to this invariant combination. Once you exploit the observational implication of this theta bar term, you realize that you have a non-vanishing electric dipole moment for the neutron, and this electric dipole moment is proportional to theta bar. This is the prediction, and this is what you need because he hasn't been observed. The experimental bound is very, very good, and in particular, you reconcile theory and experiment if this theta is smaller than 1 part in 10 billions. So this severe inequality is the strong CP problem, and this severe condition begs for a dynamical explanation. So among many solutions, the Peccei-Quinn mechanism is for sure one of the most elegant solutions. It was proposed by Peccei and Quinn in the late 70s. And it is a dynamical solution where the theta parameter of the QCD Lagrangian is promoted to a dynamical field. And it is relaxed to a small value thanks to QCD dynamics itself in a way that I will explain. So there are several explicit realizations of this mechanism, and I will not commit to any specific model until later in this talk. But let me say that all the concrete models for the axion, they share some common features. In particular, the standard model is extended to include a new global abelian symmetry known as PQ symmetry from the names of Peccei and Quinn. And it has to satisfy two key constraints. It has to be spontaneously broken at the scale FA, where FA is bound to be much larger than the weak scale, and in particular, much larger than any energy we can reach with experiments. And this global symmetry has to be a symmetry only at the classical level. It has to be violated by quantum anomalies, and in particular, the effect of the anomalous effect has to come from strong interactions. So here is a sketch of the energy scales in these theories. The scale FA that I put on the vertical axis, you see, is much, much larger than the QCD and the electroweak scale. And this is an experimental constraints on the Peccei-Quinn breaking scale. And the low energy consequence of the spontaneous breaking of Peccei-Quinn is the presence of a pseudo-Nambu-Goldstone boson known as the axion. And this axion not only has derivative couplings as every good Nambu-Goldstone boson, but also this dimension 5 operator that I put in the box here with Gigi dual. And this operator is, of course, a consequence of the fact that the Peccei-Quinn symmetry is only a symmetry at the classical level, and it has an anomaly due to QCD. So as it is conventional in the literature, I will take this operator as the definition of the dimension 1 parameter FA. So FA is the coefficient of this operator once I normalize with alpha strong over 8 pi. Okay, so that's what I mean by FA. FA is referred to as the axion decay constant or the Peccei-Quinn breaking scale. I will use these two names, both of them during my talk. That's what I mean. Okay, I mean FA defined as in this operator, and it will appear a lot in my plots. This scale. So the way the strong CP problem is solved, once the strong interactions confine, an axion potential switches on once QCD gets strong. And in this box, I only reported the harmonic approximation of the axion potential. So I take quadratic fluctuations around the minimum, just because I want to introduce another important parameter, which is the axion mass. But the important point here is that the strong CP problem, the minimum of the axion potential is CP conserving, and so the axion relaxes towards its minimum by QCD dynamics itself, because this potential is generated by QCD, and the evolution of the axion across the universe is such that the axion will move towards the minimum, and the minimum is CP conserving. So the reason why we do not observe a neutron electric dipole moment is because the axion field value, not the theta parameter anymore, now it's a dynamical field. It's small because it was driven to that value. Let's discuss a bit more about the properties of this field. Here I put an equation where you see the connection between the scale FA and the axion mass. The axion mass is proportional to the inverse axion decay constant. I put a typical value of 10 to the 9. That's what you expect for reasons I will explain shortly. And you see that the mass range you expect is around the milli-electron volt scale. So this FA could be 10 to the 9 or 10 to the 8 or 10 to the 10. These are the numbers I have in mind. So we are talking about something much, much lighter than the electron-volt scale. Okay. So the QCD axion is very light, in particular, much lighter than any standard model particle, with the, of course, the exception of photons and neutrinos. And in particular, much lighter than more conventional dark matter candidates. For example, if you think about WIMPs or even sub-GeV thermal produced particles, here we are really in a different mass range. What about its couplings? There are two main classes of couplings. There are couplings with the gauge bosons, so the first term in this Lagrangian, and then there are coupling to fermions. So let's start from the first. We need the coupling to the gluons. They are needed to solve the strong CP problem, and maybe we have similar ones with electroweak gauge bosons. The one with electroweak gauge bosons are model dependent. They may be present or not. The one with photons is very difficult to suppress because it gets also a contribution from axion pion mixing with the neutral pion. So it gets a contribution from the UV theory, a contribution in the IR, and it's difficult to have it zero. And this is good because the axion photon coupling is very, very important for the experiments. And there are also coupling to fermions, and the coupling to fermions are proportional to the derivative of the axion field. And this is consistent with the Nambu-Goldstone nature of the axion. So there is a shift symmetry that needs to be preserved. The important point here is that all coupling are suppressed by the scale FA. This is also a consequence of the Nambu-Goldstone nature of the axion. And so the axion is a very elusive particle because all couplings will be suppressed by this large mass scale. So this slide describes the QCD axion, but especially in the recent years, people have been working not only on the QCD axion, but more generally on so-called ALPS, axion-like particles that can arise from the breaking of other global symmetries or even from string theory. This description is still valid. The main difference is that for a generic ALP, you decouple the connection between the mass and the scale FA. For a generic ALP, the mass is, it could be something independent from FA. But most of my results, all the results I will present were derived for the QCD axion, but the generalization is straightforward if you also want to consider ALPS. Okay, so we have to deal with a very light and very weakly coupled particle. So we have two immediate consequences. The first one is that it's very hard to detect because it's very it's elusive, as I said. And a second consequence is that it can play a prominent role in the early universe. I will focus on the second aspect of the axions, not because the detection is not interesting. Actually, it's very interesting, and there has been a lot of new ideas in the last 10 years, let's say. There are experiments running, there are ideas for new experiments, and that's also something very interesting that is going on. But I will focus on the second part because it's the one I work on in the last couple of years. I will start the description of axions in the early universe from the so-called cold axions. This is not the thermal population that was referred to in my title, the one I worked on, but I think it's important to review why we like the QCD axion so much, because besides providing an elegant solution to the strong CP problem, it is also a viable dark matter candidate. So this is important also because it will help us in identifying a preferred region of the parameter space from the requirement of reproducing the observed abundance of dark matter. So let us see briefly how axion dark matter works and how we identify such a region. So the axion field evolution in the early universe is described by this differential equation, the first equation here. It's the equation of a harmonic oscillator with a temperature-dependent frequency, so time-dependent frequency, because in the early universe, time and temperature are connected. And this temperature dependence is provided by QCD dynamics. And moreover, there is a friction term proportional to the first derivative of the axion. And the constant h appearing in this equation is the Hubble parameter. So it's the expansion rate of the universe. And on the left of the equation, there is a plot that describes the axion field evolution in the early universe. And it has two main phases. So at the very beginning, it is stuck by Hubble friction. So the friction term in this harmonic oscillator wins over the force, over the term proportional to the mass. And initially the field doesn't move. And then it undergoes damped harmonic oscillation. So damped by the Hubble expansion, the energy density is diluted because the universe is expanding. And the redshift of this energy stored in the axion field has a redshift behavior, which is the same as cold dark matter. So we have solved this equation, and we have a connection between omega axion h square. Omega is the density of the axion expressed in dimensionless units. So it's the axion density divided by the critical density. H square is the Hubble parameter in some conventional units.
I have a question.
Yes, of course. Please ask questions, all the questions you want.
First, with respect to the action in general, you are sort of taking a small value of theta. Now you have a small value of the mass of the action. So it seems that you haven't accomplished a lot. I mean, I know that people use that, but isn't there a sort of seesaw mechanism that gives you a small value of the action mass or something like that? Because otherwise it's a problem, naturality problem, no? In general,
so the question is about this theta initial value.
The mass of the action, I mean, it's very, very small. And
this equation here.
Yeah, you are sort of putting one problem into another. No? Why so small?
Oh, the reason why it's so small is because the Pecha-Quinn breaking scale is large. But that's not a fine-tuning. It's not, there is no cancellation. I'm just saying that the new physics is heavy, as large as 10 to the 9. So the axion mass is suppressed by this number, and that's the number you get. So you have a hierarchy between two scales, the QCD scale and the Pecha-Quinn breaking scale. But you are not setting any dimensionless number to a very small value. You are just assuming that there are different energy scales in nature.
Oh, okay, but the other question is, shouldn't you have a sort of Boltzmann's equation? Because this looks a very, very simple equation. I mean, shouldn't it have something more complicated?
Good, okay. Good question. So this is the equation describing the axion field, the zero mode of the axion field. So it's a Bose-Einstein condensate. And I will discuss about the thermal population, and I will give you Boltzmann equation in 3 or 4 slides. Okay, so for now I'm describing the zero mode of the axion field, and then I will describe the rest. That's the thermal population I studied.
Okay, thank you.
So there are 2 separate populations. Very good. Okay, other questions? Okay, so we were at the equation for omega h squared. Omega h squared is the axion energy density, and we want this number to be 0.12. So I normalize it to 0.1 here, and we see that it's proportional to FA, to some Funny power, this is just a consequence of the dependence of the axion mass with the temperature. And then the initial field value, because when we have a differential equation, we also have to set the initial condition. Theta I is this variable here, the axion field defined in units of Fa, and we don't know this initial value. So in order to proceed and to compute the axion density, we need to know how to set the initial field value. So there is a nice interplay with the physics of inflation, because it depends. It depends if the Pecek symmetry was broken before or after inflation, and if it was broken, it depends if it was restored afterwards. The first case, so there are two main scenarios. The first case is the so-called post-inflation scenario. This is the situation when inflation happens at a very large scale, much larger than the Pecek breaking scale. And basically you have Pecek breaking after inflation, and you decouple the physics of inflation. So what happened here is that you need to average over all possible initial field values. So in principle, this equation, you take an average over all possible theta I, because the initial field value is selected stochastically at the Pecek transition, but then the horizon is much smaller at the time, much smaller than the horizon today. So now we live in a region of the universe, in a patch of the universe, where this theta I value takes all possible value. So we need to average. So in principle, omega h squared depends only on Fa, but unfortunately, there are additional contributions from topological defects, and so there is a significant uncertainty in the final value. So what you see in this plot, which I took from this reference, you have Fa or Ma on the two horizontal axis, pick the one you like, theta I on the vertical axis, and this red band is setting the size of our uncertainty. Okay, so you see that if you want dark matter, you need to live with Fa between 10 to the 9 and 10 to the 11. The other situation is when you break Pecek after inflation. So, sorry, before inflation. So it's the pre-inflation scenario. So in this case, within our current horizon, there is only one value of the axion field. So the bad news is that we don't know this value, and so the axion density depends on two parameters, the initial field value and the Pecek decay constant. The good news, though, is that the topological defects get inflated away from inflation, so we do not have that extra annoying contribution. We can just focus on the zero mode, the so-called misalignment. And so this is the equation that gives you the parametrics of this line. So if you are in the pre-inflation case, you have to live along this line. You see that unless you're willing to pay a price to set this initial field value to a very small value, so after all, we are trying to understand why theta today is so small. We want to make it small by dynamics, but not to set it small since the very beginning. Okay, so it's natural to say that even if we are in the pre-inflation scenario, we like to live here with theta initial of order 1, and you end up in a region of F which is similar. Okay, so this review, this brief review on axion dark matter was to describe quickly how axion dark matter works, but also to identify a preferred region for Fa. This region is between 10 to the 9 and 10 to the 11. It's the region where it's reasonable to have axion dark matter. It's not the only region, even if Fa is larger or smaller. There are plausible cosmological histories where you can have axion dark matter without any problem. Okay, so this is just I put here that there are caveats. Okay, I don't want to argue that this is the only region, but this is just an idea of where we should expect a reasonable range for FA with caveats. Okay, so I leave it like that. Okay, so now if there are more questions about the strong CP problem, axion dark matter, this is a good moment, because this ends my intro overview on axion as a solution to the strong CP problem and axion dark matter, and I will focus on the thermal axions or hot axions for a reason that I will explain in a second, which is the contribution that I gave in the last couple of years. So I don't see questions.
Well, I don't understand very well why this had to happen during inflation. Why it couldn't happen after that? I mean, what was the reason?
It could happen before or after. We don't know. We don't know. Okay. It depends on the energy scale of inflation, on the value of FA. These are all numbers that we don't know at the moment. So we need to be willing to accept both for now, unless we know the energy scale of inflation and the axial decay constant, and then we can compare them and see what happened first. But I mean, these two scenarios are equally plausible. Well, people might prefer one or the other, but there are no objective reasons to exclude one of them now. Okay. So now I come to the part of axion cosmology where I produce recent results. I discussed in the title, I used the expression thermal axions, but here I want to describe them as hot axions, just to be compared to the cold axions, which is the population that accounts for cold dark matter. So by hot here, I mean axions that are produced with kinetic energy much larger than the mass. And so these axions are relativistic at production. So I will focus on the thermal production of hot axions. So I want to produce axions that are hot, so they have kinetic energy much larger than the mass. And I want to produce them from scatterings or decays involving particles belonging to the primordial thermal bath. Primordial thermal bath, I mean standard model particles in the most minimal extension, so all the particles we know very well. And as I described at the beginning, the axion couples to these particles. It couples to gauge bosons, it couples to fermions. And so I like to think about this thermal production as the unavoidable production, because it only relies upon the existence of the standard model thermal bath and the coupling between the axions and the standard model fields. So for every specific UV complete axion model, the amount of hot axion produced thermally is fixed once we fix the couplings, unless we assume that something strange happens in the early universe. If you commit to a standard cosmological history, this is unavoidable. So there could be decays or scatterings. Here I put a B1, B2, B3. By B1 and B2, B3, I mean just a bath particle. So this could be a top quark, could be a gluon, it could be a whatever. Okay, standard model particle. B stands for bath. Okay, it's not the B meson. So axions produced in this way are clearly relativistic, because I will consider these processes from the thermal bath, and you know, the lightest standard model particle that coupled to the electron, the lightest fermion is the electron, which has a mass of half of MeV, more or less, and the axion mass is below the EV. So these bath particles needs to be around, so the temperature has to be larger than the standard model particle masses, and so the axion gets a kinetic energy that is more or less equal to the temperature of the universe at that time. Okay, that sets the energy scale. So after they are produced, they may thermalize or not. So this reaction could go also from right to left if you make enough of them. If you don't, they just redshift with the expansion, so they lose energy because the universe is expanding. And maybe they will get non-relativistic at some point, but this will happen quite late, once the temperature gets around the axion mass. So they are for sure relativistics at BBN, and they are likely to be relativistic at the recombination. Yes?
This is new is a neutrino, is that?
Right, there is also the neutrino case, good question, but if you take the axion coupling that I showed you here, so you need a derivative because it's a Goldstone boson. Yeah. You can do a by-part integration, and you see that the coupling is proportional to the fermion mass. Mm-hmm. So coupling to neutrinos are very, very suppressed for the axion. They are suppressed by a factor of neutrino mass over Fa. And so they don't contribute to this production. So that's why I'm considering only the lightest one I'm considering is the electron. Okay, so we have extra radiation at BBN and CMB formation if you produce these axions. And historically, this extra radiation is parameterized as delta N effective. So in terms of an effective number of additional neutrino species, this is the well-known relation to quantify delta N effective. So here is an interesting plot which tells you how well we can probe this extra amount of radiation. So here I'm assuming that, let's take the green line. The green line is for a scalar. Scalar means one internal degree of freedom. The axion, technically speaking, is a pseudo-scalar, but it doesn't matter. Here I'm just counting the degrees of freedom. So delta effective on the vertical axis is a function of the temperature when this new degree of freedom decouples from the thermal bath. So I'm assuming that at some point it was coupled. You see that Planck, the current bound, is probing particles that they decouple around the QCD phase transition. And in the future, these CMB stage 4 experiments will probe particles that decouple as early as the electroweak phase transition. That's the goal, the target of these experiments. This is also the chance for me to acknowledge my collaborators. They are my two postdocs at the time when this paper was released. So Fazlullah Ajakarim, who just joined University of Oklahoma as a postdoc, and Seokun Yoon, who is still in Padova, but just for 2 more weeks, then he will go back to Korea as a faculty member. And they were really, really important to get the results I will present to you. So I described this plot, and you know, it's important that we get the prediction right, because if you miss the decoupling temperature by a factor of a few, you see that this green line is changing a lot here, just because the number of degrees of freedom of the bath is changing, okay, because particles are going non-relativistic. So what we do is to, what we did, and what I will show you, is to compute the axion production rate and then solve the Boltzmann equation for this axion population. So that goes back to the question that was asked before. I will present our predictions for delta N effective that we obtain by solving a Boltzmann equation. And the only tricky part for the Boltzmann equation before we solve it is to compute the axion production rate. So I will present first the calculation for the axion production rate and then the prediction for delta N effective. Okay, so the calculation of the collision rate in principle can be done for each single operator. And that's what has been done in the references in the first block. And I am in several of these. And I was not very happy with this because, of course, it's the simplest thing you can do. You just couple the axion to one field, and then you compute the rate and you solve the Boltzmann equation. But this situation is not realistic, because once you write down a UV complete model for the axion, it's likely that there are multiple couplings that contribute to axion production. And if you want to quantify axion production for a full UV complete model, you have to compute axion production rate across the entire expansion history. And that's what we did in this paper here, this paper from 2 years ago. And we studied the axion production rate for the KSVZ model and the DFZ axion model. So these are the two most popular UV completions for the axion, and they are different just from the way you implement the color anomaly. So in the KSVZ axion, the color anomaly is due to the presence of some heavy colored field that carries a Pechequin charge, and all the standard model fermions are neutral under Pechequin. On the DFZ case, the case is the opposite. You have no new fermion, but the standard model quarks are charged under Pechequin, and that's why you get the anomaly. Okay, so before I get to these recent results, I would just like to advertise these two papers. And we studied the situations where the axion coupled only to leptons or only to the third generation quarks. The reason why we did this first is because these cases are easier. So if you couple to leptons, you don't need to worry about QCD in the early universe. Okay, all of these scattering rates, there is only QED or the electroweak interactions involved. So it's very simple. And for third generation quarks, there is QCD, but the top and the bottom are heavy enough that you can do perturbation theory and not worry too much about confinement. You are far away enough. The bottom mass is almost 5 GeV that you can forget about confinement and do a perturbative calculation. So these two cases were simpler. And the results we found were interesting because in the case of coupling to leptons, we did a fit to the Planck data, and we found that this contribution could actually alleviate the Hubble tension. So the presence of this extra radiation can improve, not completely erase the tension, but just improve a little bit. And for the third generation quarks, we pointed out that the future CMB experiments can test these couplings, and they will in a region which is not excluded, but they will be probed by future axion helioscopes. So we identify this region between 10 to the 8, 10 to the 9, and also 10 to the 10, where perhaps you have dark matter, you are on the edge, but these vertical lines are experiments probing axions coming from the sun, producing the sun and detecting on the Earth. CAST is excluded. IAXO is the future prospect. And you see that this region is very interesting because it will be probed by the future helioscopes and by the CMB as well. Okay, now let me get to our more recent study. So the KSVZ axion is, as I said, the model where you have that the Pechequin anomaly, the color anomaly, is due to the presence of this heavy Pechequin fermion that they call psi, which is colored and which carries a Pechequin charge. So here is the result from our paper. And the result is the production rate. So this is gamma A. It's what goes on the right of the Boltzmann equation. And I present the results of gamma A times FA squared because the dependence on FA is trivial. So all the scattering cross-section will go like FA to the minus 2 because each process has an amplitude that goes like 1 over FA. The axion, you produce one axion. Every time you produce one axion, there is a price to pay in terms of 1 over FA. So here is the result, and you see that there are thresholds across which the rate changes. So there is a threshold of these heavy fermions that we set to 10 to the 5 GeV here, and the rate change the slope. And then we also address the issue of the QCD phase transition by approaching both sides with perturbation theory, and then drawing an interpolation in between. From this expression, from this result for gamma A, we can plot delta N effective predicted as a function of FA. Let's focus on the red line. These different lines just correspond to different initial point of the Boltzmann evolution. So the red line is when we start the evolution to high temperature. And you see that this vertical line is what is excluded by stellar physics. So the supernova bound on the axion excludes Peche-Quinn scales of 10 to the 8 or so. But you see that you are going to produce enough axions, even in the region where you're not excluded, enough to be tested by these future CMB4 experiments. So that's the first result. Now, we also did the DFSZ, and DFSZ, again, there are no new fermions, there are two Higgs doublets, okay? So this model is a bit more complicated because there are lots of processes. The axion basically at low energy couples to everything. It couples to the Higgses, it couples to the fermions, all of them. It couples to the gluons, to the electroweak gauge bosons, both the W, the Wi and the B, the SU2 and the U1. So if you want to compute the rate, you have to sum over lots of processes. That's what we did, and that's what we found. So the plot, the notation is identical to the previous one. You have gamma FA squared, and you have the temperature on the horizontal axis, and the black line is the rate. So there is an additional parameter here, tan beta. Tan beta is the ratio between the VEV of the two Higgses. Is like the same in supersymmetry, okay? So you need the two Higgs doublets here. And the rate doesn't depend much on tan beta. So we can make predictions here. We, for the purpose of illustration, we set tan beta equal to 10, but if you look at this plot for tan beta equal to 3, for example, nothing changes. The situation here is a bit more difficult because on top of the supernova bound, you also have the bound from white dwarfs. The bound from white dwarfs is due to the fact that the DFSZ axion also couples to the electron. And so if you couple to the electron, you have additional stellar bounds that constrains your model even more. But you see that there is, well, first of all, is these stellar bounds, they come with caveats. So we are producing something independent from stellar physics. In our framework, we only rely upon the CMB. And you see that there is a tiny region which is still not excluded, and it can be probed by future CMB stage 4 experiments, although it's not as large as the one in the previous figure. Now, all of these plots where I predicted delta and effective as a function of FA, and I use the CMB bounds, these plots make sense if the axion mass is small enough that it can be treated as radiation at the CMB point, at the CMB formation. Okay, otherwise it's wrong to describe the axion as a contribution to the additional number of neutrinos. So you see that, I mean, I want to be on the right. Let's go back to this plot, okay? So the axion mass is almost 10 to the minus 2 electron volt in the interesting region. The CMB temperature is 0.3 electron volt. So it's interesting that 0.3 electron volt, if you look at this plot here, is more or less where you have the Planck exclusion bound, okay? So what we're doing is fine, because if you look at this line on the region not excluded by supernova, the axion is light and delta ineffective is a good description. But what if we want to use a Planck exclusion bound? We cannot use delta ineffective because we enter a dangerous region for the mass. So that's why we did this more recent study, where we joined a team of cosmologists that were doing these studies on the axion mass already. And our contribution was to bring these updated production rates. And we did a complete and self-consistent study of axion cosmology starting from production. And then we studied the BBN, the modification of light elements abundances, the implication of this modified helium abundance on the CMB, the implication of CMB formation with axions, baryon acoustic oscillations. So we started from the beginning to the end. And the output of this analysis was a bound on the axion mass, which is, as you can see, for both the KSVZ and the DFSZ, it's very, very close to the recombination temperature. So you cannot simply treat the axion as being an additional radiation component. The effects from the axion mass are very important, and we implemented them here. So the two bounds you see are 95% and 99% confidence level. That's why you see two of them. And you see that the bound is stronger for the DFSZ. The reason is that you have more production channels, as I was discussing. The DFSZ couples to more particles, in particular to the electron that makes axion production efficient until later times. That's why the bound is a little bit stronger, but not too much. Okay, so you're between 0.2 and 0.3 electron volt. Okay, so the last thing I want to discuss is also something very recent that I did with my postdoc Seokun Yoon, and it is about other models, other axion models, where you have coupling to fermions that are off diagonal in flavor space. Okay, so you see in this combination of couplings, psi I and psi j, these are fermions of different generations. And in particular, I restored the vector current because the vector current is vanishing only if you have a diagonal piece. But if you have an off-diagonal piece, of course, if you integrate by parts, you don't get zero anymore. So these flavor violating axions are the target of several experiments on the Earth, searching for rare meson decays. And they're motivated because some models trying to connect flavor with Pechet-Quinn symmetry, they naturally arise. So we wonder about the role of these axions in the universe. And as you can see from the summary in these plots, the green exclusion bands are present in future exclusion bounds from cosmology, and the color one are from experiments on the Earth, like mostly rare meson decays, and I put the caption to each one of them. And you see that cosmological bounds are competitive or sometimes even better than the one from the lab. This is true about current and also about future projections for these bounds. So this study came out only last year, and we did the analysis at the level of effective operators. We switched on one operator at a time, but we think it's very interesting what we found, because we found that cosmology can even do better than lab sometimes. And so we are currently studying some specific UV completions for these flavor violating couplings and see how well cosmology can do compared to the terrestrial experiments. So I come to my conclusions. I told you about the Pechet-Quinn mechanism as a solution to the strong CP problem. The low energy consequence is the QCD axion. It's a very appealing scenario because not only you solve the strong CP problem, not only you have a dark matter candidate that can explain why we observe this abundance of dark matter, but it's also very interesting because it's testable. It's testable. There are many experiments searching for the axions on the Earth, but there are also many cosmological surveys trying to look for a hint of the presence of the axion in the early universe. Something I didn't mention at all today, but it's also very interesting. The Pechet-Quinn phase transition can source gravitational waves, for example. And that's another consequence of the Pechet-Quinn mechanism. So the most famous consequence, of course, is the production of dark matter. So in this plot, there is the summary of cold axions, but it is far from being the only one. So today I told you about thermal axion production in the early universe. The population of relativistic axions is unavoidable, thermally produced. It's unavoidable because we have a thermal bath, and it can leave an imprint in the CMB. And I showed you the predictions for the two most famous UV completions, the KSVZ and the DFSZ. There is also an intriguing interplay with flavor physics that we just started to exploit. And also, if you want to analyze the current data seriously, unfortunately, the axion mass that you are testing is dangerously close to the CMB temperature at recombination. And for this reason, we had to do a complete analysis to put a bound on the axion mass. And that's here I also put the plots of all the correlations among the observables, and that's basically how we got the bound on the axion mass that I quoted before. So thermal axions are a complementary probe of the Pechet-Quinn mechanism that can unveil the presence of the axion in the early universe, together with, of course, the abundance of dark matter, and so they could confirm the presence of the axion if discovered. So before I conclude, let me say that, as I was mentioning at the beginning, it's a pleasure to being back in Valparaiso, even though I'm only there virtually. So I hope I can come back in the future. Here, I told you I took this picture on the 31st of December 2018. I was there, and I had a fantastic trip to Chile a few years ago, and I hope to come back soon. So thank you very much.
Thank you very much, Francesco, for the excellent and very complete talk. Question from the audience? Mauro Cambiaso, please. How do you have question?
It's just clapping. I think it's clapping.
Yeah, it was only that. Thank you very much. Nice talk.
Thanks. Thank you.
Question from the audience?
I have a question. Do you hear me?
Yes.
Okay. Thank you for the presentation. My first question is, so provided you have, let's say that the cold dark matter is an axion, so it's always, do you expect hot axions produced from the thermal bath, or there is a condition for the occurrence of that?
So the presence of the axion from the thermal bath, I expect them if the axion couples to the thermal bath, but we know that he has to couple to the thermal bath because he has to couple at least to gluons if we want to solve the strong CP problem. So I expect that because the axion is coupled to the thermal bath. Of course, there could be one caveat. If you have inflation with a very, very low reheating temperature, then there is no bath because you reheat the universe at a very, very low scale. That's the only caveat that can come to my mind. But if you have a thermal bath that existed at least at temperature as large as the weak scale, that's unavoidable. Even if the Pechet-Quinn scale is at the Planck scale, you expect? Yes. Of course, the amount of hot axions you produce depends on the size of FA. So if FA is at the Planck scale, the scattering rate are too small. Okay, and then you basically make no axion. So if you remember, I can show you my plots. You see, you produce these only if F is 10 to the 10. So you see that all the predictions go to 0 if F gets too large.
Okay, okay.
So I expect that unless f is very large, of course, then you decouple the axion if f is large.
And my second question is with respect to this equation of equilibrium chemical, or the moment of the decoupling of your thermal axion, and you put this B1 plus B2 going to B3 plus the axion.
Okay.
So this is a chemical decoupling, right? So my question is, what are the conditions that for the occurrence of this? Because in principle, in thermal equilibrium, you expect the rates in the forward and the backward directions the same, right?
Yeah. So first of all, this reaction may even never be in equilibrium. So it's possible that B1 and B2 collide enough times to make some axions, but not enough to thermalize. The axions you make will survive, okay? So it's a channel that is, it's like dark matter freezing, okay? Then if you make enough axions, you eventually thermalize. So this arrow goes from left to right, right to left, both directions. Eventually you reach a freeze out point, and as you correctly say, it's chemical freeze out. So the condition is gamma equal H to have this decoupling. So the production rate is equal to the Hubble expansion rate.
Okay. Yes, you compare with the Hubble rate.
Yeah. So we solve the Boltzmann equation to be more precise, but if you want a naive estimate, you can do gamma over H, and you get more or less the size of the effect. If you don't care too much about precision, you can do that.
But in order, if you start with this equilibrium, this chemical equilibrium, let's say that the axions are thermalized, so the reactions to the left and to the right are at the equal rates. In order to have now only to the right, you expect some Boltzmann suppression in B1 and B, in B3, for instance.
Yes. So the reason why you go out of equilibrium typically is because of the Boltzmann suppression. So imagine that these B1, B2, and B3 are the top quarks and the gluon, for example. It's like TT bar going to gluon and axion. If the temperature is larger than the top mass, you're fine. Once the temperature gets below the top mass, B1 and B2 are exponentially depleted because of Maxwell-Boltzmann. And so you get a freeze out because the rate becomes too small due to this suppression.
Yeah. Okay.
So that's what happens. Of course, if the coupling is large enough to have them to scatter, but if the coupling is large enough, that's not enough, because then you have to pay an exponential price that will bring you out of equilibrium. It's like for the WIMPs.
Yes. Okay. Thank you.
You're welcome.
More questions? Francesco?
Yes.
A comment question. Can you please comment a bit more about the bound that you get from this rare process like electron muon conversion of mu gamma in the last slide that you show the constraint of imposed by this process in the axion couplings?
So I didn't explain the details of these plots, so I can say a few more words. So here, for example, let's take the leptonic flavor violation, which is the simplest one. Simplest because there are less lines. So let's look at the last row. And here is a bound on the coupling where you violate the flavor and you couple the axion to the tau and the muon. Okay. So the orange band, and sorry, on the horizontal axis, there is F, capital F is like small f divided by C. Okay, so it's the inverse axion coupling. So you can express that in GeV. So you see that the orange, you have two orange bands. So the dark orange is current bound, and the light orange is future bound. And here you have the dark green, which is the Planck bound, and the light green, which is the CMB, which is stage 4, so future bound at 2 sigma and 1 sigma. So you see that if you compare the darker bands, cosmology is providing you with a better bound than the collider, the experiments on the Earth. Okay, the search for this rare tau decay. And even if you look at the future, then you see that cosmology will still do better than these searches, because the faint bands, the green still provide you a better bound. Okay.
Okay.
So that's for each pair of green and color bands. Here I'm showing a different coupling, and that's the spirit. Okay, that's how you should read the other lines. Okay, the dark bands are the present, and the faint bands are the future, and the green ones are cosmology.
And here, when you put plus invisible, you consider not only tau mu gamma or mu e gamma, but also electron muon conversion in nuclei. You consider as well.
For the tau coupling, no. I don't think so. I mean, this is just tau going to mu and nothing else. What they look for.
So you expect if you consider also bound from tau mu gamma or mu e gamma electron muon conversion, the constraint imposed by Charleston flavor-relating processes will be weaker than those one imposed by cosmology.
No, tau going to, for example, tau going to mu gamma, it's a different signal, because it's a different coupling, no? Because I'm searching for the low energy consequences of this operator here. And this operator will give me a decay with invisible energy in the final state, because the axion is invisible. So the one with the gamma in the final state, it's a different constraint.
Thank you, Francesco. Thank you
Very
very much.
welcome. You're very welcome. My pleasure. My pleasure.
More questions from the audience? If there are no more questions, we thank Francesco for the excellent and complete talk. We see you at the next seminar. Thank you so much, Francesco.
You're welcome. Thank you for inviting me. Have a good day.
You're welcome. My pleasure.
Thank you.
I hope that you can come back to Chile soon. I think in 2 years we will have the biannual conference. It will be great if you can come soon to Chile.
I would love to. Good. Okay, let's plan to do that. Very good. Okay. Yes. Thank you. Bye-bye.
Bye. Bye. Bye.